we're going to go outside the prerequisites. We're officially outside the prerequisites of this course now. So what we're going to do is think about the relation between the electric and magnetic fields, or rather just the electric fields in this case, above and below a boundary with electronic properties mu and epsilon, okay? So if we're going from vacuum to glass or something, or glass to water, and we're going to look at the field right above the interface in the water compared to the electric field in the glass. We're going to apply Maxwell's equations to do this. This is beyond the scope of the prerequisites of this course, so I'm not expecting you to memorize this. If you want, skip forward a minute 30, fine. But I just want to derive what we have so you can see that we're not pulling them out of thin air. So if I have a boundary, imagine that I had I have some boundary, and here's my attempt to draw a three-dimensional surface. And above it, we have mu1 and epsilon 1. And below it, we have mu2 and epsilon 2. What is the relation? I'm going to look at the field in the limit right above versus right below. Okay, so right above this, I'm going to have some electric field, E1. And right below it, I'm going to have another electric field, E2. And remember, the electromagnetic field is just something that permeates all space. So it's going to, I can take this distance to 0, and it's just going to be some continuously changing electric field here, or rather this electric field that I can run my finger along and see how it changes across this boundary here. All right. So we're going to use the Maxwell equation that we showed last time, that the divergence of the displacement field was equal to 0. Okay. Now we're stepping outside our comfort zone a bit, but that's all right. Let's see what we can do here. We're going to use this and use something called Gauss's theorem, or the divergence theorem. It tells if I take the volume integral of a region of space, that's going to be equal to the area, the surface integral of the boundary of that region. Okay? And in this case, that's going to be equal to 0. This is Gauss's theorem. This is not part of the course, but I'm just gonna show you this derivation. So this is the divergence theorem, and we're gonna use a very particular surface here. We're gonna use a small little cylinder, and we're gonna take this. We're gonna look at the divergence, the displacement field dotted with dA, the normal to the surface, for this region here. And what we're gonna do is we're gonna take the limit as the sides go to 0. So if I just write out this integral, this area here, what is the area? Well, it's going to be the integral along the sides of d dot, it's going to be the xy, we'll just call it the r hat, dr hat, the part that the flux that's going kind of transverse here, right? Plus the top, the area on the top, d dot dA, plus the integral on the bottom. This is that flux coming out of that other surface, and that has to be equal to 0. This is what this divergence theorem tells us. And what we're going to do is we're going to take the limit as the height of this thing, we'll call it h, as the height goes to 0. Okay, the limit of the height goes to 0. This term is going to cancel out, right? Because the area is going to be squeezed to nothing. The top, however, is not, right? We're going to have some finite amount of area on the top because we're just taking the limit as the height of the cylinder goes to 0. And as we get to 0 height, basically we're just looking at the value of d pointing out of it, which is, we're going to call that the perpendicular part, the part of d that's pointing out the top, times a, that's all it is, plus the part that's on surface 1, plus on the bottom, d perpendicular to, times, well, it's pointing the other way, so this dot dA here is going to give us a minus a, and that's equal to 0. The a's cancel, so it just tells us that d1 perp is equal to d2 perp. And using our relation between epsilon and e, we have epsilon e1 is equal to epsilon 2, epsilon 1 E1 is equal to epsilon 2 E2, perp. So that we have a relation between the perpendicular components of the electric field directly above. This is interesting. We have separated, we can now separate the field into, here's some random field right at the surface. It's going to have a part of it which is perpendicular to that surface, and then the rest of it, which is going to be the part of it which is parallel to that surface. Okay, so let's just rewrite this first result here. All right, how about the other part of it? Well, we're just going to take another surface and use another one of these equations from vector calculus that you'll learn in your math classes. And that's saying that if we take another kind of surface, we're just going to move a very, very small or short rectangle around the surface there. And we're going to use another theorem that says if we have a cross product, which in this case is equal to d by dt of B, right? This is one of Maxwell's equations. What we can do is we can take the area integral, the area of this surface, and Stokes' theorem will tell us that this is actually equal to E dot dl integrated around there. And this is going to be negative d by dt B, well, integrated around the area, right? The amount of magnetic field going through that area. And we're going to do a very similar trick to last time. We're going to take the limit as the height of that triangle goes to 0. We'll call this the height. We'll not neglect the length. We'll just take the limit as that gets squeezed to like an infinitely short rectangle. So what we get there is, again, if we just do this, we're going to get E perpendicular times L minus, when we go the other way, the E perpendicular on the bottom times L plus the sides is equal to negative d by dt times our area, whatever that area is, that dot product of the integrated area. But in the limit as h goes to 0, the sides are going to go to 0 because the length of those sides goes to 0, as well as the area of this rectangle here. So we just wind up with the result that E1 perpendicular times L is equal to E2 perpendicular times L. The L's cancel, and we have our boundary condition for the other field. Okay, and this is our electromagnetic boundary conditions here. Okay, so we can just write, we can turn this into more of an optics-y thing by incorporating the index of refraction. So just using what we had before between epsilon and epsilon naught, we can write the epsilon in terms of epsilon naught of the index of refraction squared. And doing that, inserting it, we get this relation is actually just tells us that E1 perpendicular is the ratio of the indices of refraction squared times E2 perp.